Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The collective body of experimental work completed during 1942 by the team under the direction of Theodore Seaborg concerning the new element, plutonium, represents a landmark in the history of science, a period of intense, mission-driven discovery that forever altered the course of human affairs. The research, conducted under the utmost secrecy within the metallurgical laboratory at the University of Chicago, was a compressed epic of scientific deduction, moving from the confirmation of nuclear properties on an invisible scale to the isolation of the first tangible speck of a synthetic element. This essay provides a profound evaluation of the internal claims, methodologies, and logical frameworks presented in the sequence of classified reports and experiments that constitute this monumental undertaking. The analysis will proceed through the key investigative phases of that year, treating each as a discrete section of the overall scientific argument, thereby illuminating the rigorous chain of reasoning that led from a theoretical possibility to a physical reality with immense strategic implications. The focus remains steadfastly on the claims, as they were formulated and defended within the context of the 1942 program, assessing the evidence presented and the ingenuity of the methods devised under unprecedented pressure. Section 1. The confirmation of a high fission cross-section for plutonium-239, the initial and most crucial claim advanced by Seaborg's group in early 1942 concerned the fundamental nuclear behavior of the primary isotope of interest. The central assertion was that the isotope of plutonium with mass number 239 possesses a large cross-section for fission when interacting with slow, or thermal, neutrons, and that this cross-section is significantly greater than that of uranium-235. This claim was the sine qua non of the entire enterprise. Its verification would elevate plutonium from a mere chemical curiosity to the core of a potential atomic weapon. The methodology employed to substantiate this claim was a testament to the team's experimental acumen. The process began with the creation of the plutonium-239 sample itself. Uranium oxide was bombarded with neutrons from the 60-inch cyclotron at the University of California, Berkeley. This bombardment transmuted a fraction of the uranium-238 into uranium-239, which rapidly underwent beta decay to form neptunium-239. This neptunium isotope, with a half-life of approximately 2.3 days, subsequently experienced another beta decay, wherein a neutron in its nucleus transformed into a proton while emitting an electron, yielding the target isotope, plutonium-239. The quantity produced was infinitesimal, on the order of micrograms. The chemical separation of this trace amount of plutonium from the bulk uranium and a complex superfission product was itself a major achievement, relying on early tracer studies of plutonium's chemical behavior. The isolated sample, electroplated onto a platinum disc, was then transported to Chicago to test the claim. This disc was placed inside an ionization chamber positioned near the thermal neutron beam of the Washington University cyclotron in St. Louis. The experiment's logic was directive. Plutonium-239 were fissionable by these neutrons. The heavy, energetic fission fragments produced would cause large, detectable pulses of ionization within the chamber. The critical part of the evaluation involved the direct comparison of the fission rate of the plutonium sample to that of a standardized sample of uranium-235 of known mass. The evidence gathered was unambiguous. The number of fission events observed per unit of time from the plutonium-239 sample, when normalized for the quantity of material, was substantially higher than for the uranium-235 standard. The specific claim, articulated in a report to the Uranium Committee, was that the slow neutron fission cross-section for plutonium-239 was approximately 1.7 times that of uranium-235. The evaluation of this claim finds the methodology sound and the conclusion, given the limitations of the era, robust. The primary sources of potential error such as cosmic ray interference and spontaneous fission, were meticulously accounted for through extensive background measurements. The strength of the claim rested on the careful calibration of the neutron flux and the precise quantification of the comparison samples. This experimental result, confirming a high fission probability, provided the definitive impetus for the United States to pursue a plutonium-based weapon and to authorize the construction of larger-scale production reactors. Section 2. The elucidation of plutonium's dual oxidation state chemistry. With the nuclear properties confirmed, the focus of Seaborg's group shifted to a problem of immense practical difficulty: the development of a chemical process to separate plutonium from irradiated uranium on an industrial scale. The claim at the heart of this phase of the work was that plutonium exhibits at least two distinct and stable oxidation states in aqueous solution: a lower state, believed to be the +4 state, and an upper state, likely the +6 state, and that these states possess starkly different chemical affinities. This difference, the claim proposed, could be exploited for separation. The key assertion was that by manipulating the oxidation state of plutonium, it could be made to either precipitate, with a carrier compound, or remain soluble, allowing it to be separated from uranium and fission products. The methodology for proving this claim relied almost exclusively on tracer chemistry, a technique in which Seaborg was a master. Because they had no weighable quantities of plutonium, they used the radioactive nature of the element as a tack. For much of this work, they employed plutonium-238, an alpha-emitting isotope produced by deuteron bombardment of uranium. Its shorter half-life yielded a much higher specific activity, making it far easier to detect in trace amounts than the long-lived plutonium-239. The experimental framework involved adding a known quantity of plutonium-238 tracer to a solution containing uranium and representative fission products. The team then investigated the effects of various oxidizing and reducing agents. The central finding, which formed the basis of the claim, emerged from experiments with fluoride precipitation. They discovered that in the presence of a reducing agent, such as sulfur dioxide, the plutonium would quantitatively co-precipitate with a carrier like lanthanum fluoride. However, when a strong oxidizing agent, such as bisulfate with a silver catalyst, was first added to the solution, the plutonium's chemical identity appeared to transform. In this oxidized state, it failed to precipitate with lanthanum fluoride, remaining in the supernatant liquid. The evaluation of this claim finds it to be a brilliant piece of chemical inference. The evidence was indirect yet overwhelmingly consistent across hundreds of experiments. By tracking the radioactivity, they could chart the behavior of the invisible plutonium. The claim's power lay in its proposed oxidation-reduction cycle. One could precipitate plutonium with a fluoride carrier to separate it from uranium, dissolve the precipitate in acid, oxidize the plutonium, and then add fresh lanthanum fluoride to carry down remaining rare earth-like fission products, leaving the purified plutonium in solution. This proposed cycle, based entirely on the claim of dual oxidation states, was the conceptual foundation for the entire plutonium separation effort. Its formulation was a feat of chemical prophecy, sketching the blueprint for a massive industrial process based on the behavior of atoms they could only detect by their radioactive signature. Section 3. The formulation of the bismuth phosphate process. While the lanthanum fluoride process validated the core chemical claims, it presented significant practical challenges for larger-scale implementation, chief among them a highly corrosive nature of hydrofluoric acid solutions in industrial equipment. This led to the next major phase of the work in late 1942, the development of an alternative separation process. The central claim of this section of work, formulated by chemist Stanley G. Thompson, was that bismuth phosphate could serve as a superior carrier for plutonium in its reduced, or +4, state. The full claim extended to a complete, industrially viable flowsheet. Plutonium in its tetravalent state would co-precipitate with bismuth phosphate, separating it from the soluble uranium nitrate solution. The precipitate could then be redissolved, the plutonium oxidized to its hexavalent state, and a fresh batch of bismuth phosphate precipitated. In this second step, The oxidized plutonium would remain soluble, while many contaminating fission products would be carried down with the bismuth phosphate precipitate. The methodology to support this claim mirrored the tracer studies of the lanthanum fluoride work, but with a new set of chemical conditions and a different carrier. The experiments involved systematically testing various potential inorganic carriers. Bismuth phosphate emerged as the prime candidate due to its crystalline structure, which was analogous to the expected structure of plutonium phosphate, and its insolubility in strong acid solutions. Tracer experiments meticulously demonstrated that under acidic conditions and in the presence of a reducing agent, plutonium-238 was carried with greater than 95% efficiency by the bismuth phosphate precipitate. Subsequent experiments confirmed the second part of the claim upon dissolution and oxidation with a reagent like sodium bismuthate or potassium dichromate. The plutonium converted to its soluble +6 state. A subsequent precipitation of bismuth phosphate effectively scrubbed the solution of remaining impurities, leaving the plutonium behind. The evaluation of this claim reveals a masterpiece of applied chemistry, a direct and successful response to a critical engineering problem. The evidence, again derived from tracer-level radioactivity measurements, was compelling in its consistency and high yields. The bismuth phosphate process offered numerous advantages. It functioned in less corrosive nitric or sulfuric acid solutions, the chemicals were readily available, and the precipitate was crystalline and easy to handle. The claim was more than a chemical observation, it was a comprehensive engineering proposal. The selection of this process, the massive Hanford engineer works, was a direct consequence of the strength of the evidence presented by Seaborg's group. It represented a successful translation of fundamental chemical knowledge, derived from invisible quantities, into a robust industrial protocol. The intellectual elegance of the claim resided in its cyclical, self-purifying nature, which could be repeated multiple times to achieve the extraordinary level of purity required for a nuclear device. Section 4. The ultramicrochemical isolation of the first weighable plutonium compound, the culmination of the year's work, and the ultimate validation of all preceding tracer-based claims, occurred in the late summer of 1942. The overarching claim of this phase was that the element whose chemistry had been inferred from radioactive traces could be isolated as a pure, visible, and weighable compound, and that its macroscopic properties would align with the predictions of the tracer studies. This endeavour required the creation of an entirely new field of experimental science, ultramicrochemistry. The methodology was a heroic feat of chemical processing and manipulation on a microscopic scale. The starting material was several hundred pounds of uranium nitrate that had been irradiated for an extended period at the Washington University cyclotron. This material was subjected to a scaled-up version of the lanthanum fluoride separation process, a painstaking procedure conducted by a team of chemists over several weeks. The final concentrated solution, containing what was calculated to be a few tens of micrograms of plutonium, was handed over to the ultramicrochemists Boris Cunningham and Louis B. Werner. Working under a microscope, they used specially designed equipment, including micropipettes, microcrucibles, and microcentrifuges, all manipulated with micromanipulators. The final purification steps were performed in droplets of solution with volumes a few microliters. On August 20, 1942, they successfully precipitated a speck of plutonium hydroxide, the first time a synthetic element had been seen by the human eye. The more definitive milestone came on September 10, 1942, when they prepared a sample of what was believed to be plutonium dioxide and weighed it. The claim that this speck was a pure compound of element 94 was substantiated by weighing it on a specially constructed quartz fibre torsion balance designed by Paul Kirk and his student, which possessed a sensitivity of a fraction of a microgram. They measured a mass of 2.77 micrograms for their sample of the oxide. The evaluation of this claim marks it as one of the pivotal moments in 20th century science. The evidence was tangible and visible, The successful isolation and weighing of a pure compound confirmed that the entire edifice of phrasochemistry was built on a solid foundation. It proved that the oxidation-reduction cycles developed on an invisible scale worked as predicted on a bulk, albeit minuscule, scale. The accomplishment silenced any lingering skepticism about the feasibility of the chemical separation processes planned for Hanford. It was a psychological as well as a scientific triumph, transforming plutonium from a ghostly presence in the Geiger counter into a real substance, a new form of matter created by human ingenuity. There is a certain historical irony in the fact that this substance, destined to have such a powerful an influence on global history, made its first physical appearance as a barely visible smudge at the bottom of a platinum crucible in a small room on the 4th floor of the Jones Laboratory. Section 5. The preliminary determination of plutonium's macroscopic physical properties. Following the successful isolation, the immediate next step was to leverage this unique capability to make the first ever measurements of plutonium's physical properties. The central claim of this final phase of the 1942 work was that meaningful physical constants, specifically the density of the element and its compounds, could be determined from these microgram-scale samples. This data was desperately needed by the physicists and engineers designing both the production reactors and the eventual weapon. The methodology was again a triumph of microscale instrumentation. To determine the density of plutonium metal, which was first prepared a year later, a similar principle was applied to its compounds first. For a sample of known mass, as determined by the quartz fiber balance, its volume had to be measured. This was accomplished by placing the tiny, weighed sample into a fine capillary tube of precisely known internal diameter. A liquid of known density was then introduced into the capillary, and the displacement of the liquid column was measured with a calibrated microscope. From the mass and the calculated volume, a value for the density could be derived. The team also conducted solubility tests on various plutonium compounds, such as the phosphate and hydroxide, by observing their behavior in different solvents under the microscope, confirming at the macroscopic level what the tracer studies had indicated. An evaluation of the claims from this work acknowledges their preliminary nature. The first density measurements for plutonium compounds carried substantial error bars, a reality dictated by the unprecedented scale of the experiment. The value they calculated was a first approximation. However, the true significance of the claim lay in the proof of concept. It demonstrated that it was possible to extract essential physical data from quantities of material that were, by the standards of the day, almost immeasurably small. This work provided the very first data points for the metallurgists and engineers who needed to understand how this new element would behave in bulk. The claim that these properties were determinable was more important than the precise numerical values obtained at that early stage. It bridged the final gap between chemistry and physics, providing the tangible data needed to begin designing the hardware of the atomic age. Conclusion. The body of work produced by Glenn Seaborg's group in 1942 on the discovery and characterization of plutonium stands as an unparalleled example of targeted scientific research achieving its objectives with extraordinary velocity and intellectual rigor. The evaluation of the claims advanced during this year-long period reveals a chain of impeccable experimental logic. Each stage built upon the validated claims of the one preceding it, forming an unbroken sequence of inquiry from the subatomic to the macroscopic. The initial claim of a high fission cross-section provided the strategic motivation. The subsequent claim of a manipulable, dual-state oxidation chemistry provided the fundamental principle for separation. The formulation of the bismuth phosphate process translated this principle into a robust, industrial-scale claim of feasibility. The breathtaking claim of physical isolation and weighing served as the ultimate proof, a tangible verification of the entire preceding cascade of inferences. Finally, The preliminary measurements of physical properties demonstrated the power of the new ultramicrochemical techniques to provide the data necessary for engineering and design. The enduring strength of this collective work is its seamless and brilliant integration of tracer chemistry with ultramicrochemistry. The former allowed the scientists to write the chemical recipe for handling an element they could not see, while the latter allowed them to cook the meal and prove that the recipe was correct. The claims they made and defended were bold, the evidence they gathered under immense pressure was sound, and their success provided the critical pathway for the Manhattan Project, fundamentally reshaping the possibilities of science and the realities of global power.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.